Okay, so last lesson we learned about, if I remember correctly, we learned how to do the second derivative, and then we looked how it was actually, that was a lesson before that, but we looked at stationary points. We looked at a bunch of stuff, but we looked at how we can learn from the value of derivative what's actually happening in the graph. And one of the things we've done, okay, maybe I'll write it down here. We learned that you've got these places called the stationary points, the points where the graph is momentarily horizontal. And then we know, okay, for the stationary point, what do we know about the first derivative? First, on a stationary point, what happens to the first derivative? It's naught. Fantastic. We know that if for a specific place the first derivative is larger than 0, we know that the function is, or the graph is, if it's increasing, and obviously if it's decreasing, it's less than 0. Okay? Then we looked at the second derivative. And the second derivative allowed us to find out if our stationary point was a maximum or a minimum. Okay? So let's just kind of remind ourselves what's going on here. So first of all, for stationary, whether it's a maximum or a minimum, we know that, let's talk, for maximum or minimum, the first derivative must be 0. Now, what happens if the second derivative is larger than 0? Okay? Is that going to be a maximum or a minimum? Okay? What's happening really? Okay, I remember that it's a minimum. How do I remember that it's a minimum? Because what? It's a smiley face, but minimum you think is kind of, well, I guess maybe first derivative, second derivative is positive, so it's a smiley face. But if you look at what happens to the first derivative here, okay? Isn't it? The function is decreasing. F is decreasing, okay? The F is decreasing, and then it's increasing. But what I'm asking, what's happening to the slope, to the gradient, to the first derivative? And it's negative, will become closer and closer to 0, and then becomes positive. So the second derivative is actually positive. Okay, so I'll repeat that. Okay, if the first derivative is 0, second derivative is positive, then we have what we call a local minimum. Why do we call it, by the way, a local minimum? I don't think I told you. Okay, we call it a local minimum because the graph might be something like that. Now, that is a local minimum. Have a look at this. Okay, that's a local minimum. But we have smaller values of f down that side. So it's just locally, it's a minimum. Okay? The same thing of the opposite will be for our maximum. So if the second derivative is positive, that means minimum. That means negative second derivative, that must be minimum. And I guess the way to think about it is, yeah, it's negative, so it's a sad face. Okay? Okay? Sad face, happy face. Okay? But more kind of mathematically, okay, what's happening to the derivative here? Not to the function. The function goes up and then goes down. So in other words, it starts positive, getting closer to 0, and then become negative. In other words, it's decreasing. The first derivative is decreasing, meaning the second derivative is negative. Okay? And that will be a local maximum. Again, why local? This is a local maximum, but there's still values that are higher than that. But locally, it's a maximum. What we're going to do now, okay, I'm going to leave the second derivative 0. We mentioned that. We'll come to it later. Now we're going to talk about what happens when the second derivative So second derivative is still positive. I'm going back to second derivative positive. But what I'm saying here now, the first derivative is not 0. Okay? Here we looked at what's happening in the combination of these two. Second derivative positive, first derivative is 0. We know it's a local minimum. Now the first derivative is not 0. So obviously it's not going to be a stationary point. It's not going to be a minimum. But we're still going to try and find out what is it going to look like. So let's ask ourselves. Okay? It's obviously not going to be a stationary point, but what we know is that the second derivative is positive. If the second derivative is positive, okay, we'll write it down like this. I just want to make sure we can actually see it. That's a funny, yeah, you can see it, okay? Right? I'll write it down here. If the second derivative is positive. What's happening to the first derivative? If the second derivative is positive, that means that the first derivative is increasing. I'm actually writing the words. That's really important. Increasing. Okay, now what you're doing, Olivia, and hopefully the rest at home, okay, are really practicing their thinking about that's calculus at this. Okay? You know that the derivative, what is the second derivative? The second derivative is the derivative of the first derivative. So if the second derivative is positive, that means the first derivative is increasing. So now there's two options. Okay? Now I'm asking myself, what's happening to f? What would f look like? Must be decreasing. Well, it actually, I can tell you now, it can either increase or decrease. But more importantly, what does it look like? Let's look at the case when it's increasing. Or let's look at the case when it's decreasing, because that's what you mentioned. If it's decreasing, can it decrease like this? Can it decrease like that? Can it decrease like that? Which one? Not sure. Okay, let's start. Let's say it's decreasing, okay? It tells what we've written here is that the gradient is increasing. So will it look like this? Will it decrease like this? Or will it decrease like that? I'm going to pause it. I want you to really crack that one. Oops. So we had a nice, interesting discussion. Let's share it, okay? So I've drawn two values of two possible functions. We're just, at this point, focusing on decreasing f. We're going to look at the increasing f in a minute, okay? And what I'm asking myself, what happens to the derivative of f? What is the derivative? F is the slope, the gradient. So if I'm starting with the green, okay, I'm going to draw the gradient here, and let's say the gradient there, okay? Now, where is the gradient higher? And this is what was a bit confusing, okay? That is steeper, but that doesn't mean that the gradient is high. In fact, because they're both negative, both of these gradients are negative. The gradient here is more negative than there. In other words, the gradient is decreasing. It's becoming more and more negative. So this kind of decrease in f is a decreasing gradient. So that doesn't fit. It's not that one. Okay? However, if I look at the gradient here in the beginning, the gradient is very negative and it's become less and less and less negative. Okay? So that is a graph of a function that decreases, but the gradient, in fact, is increasing. It's becoming less and less and less and less negative. Okay? So I'll remind you what we're trying to ask. We're asking ourselves, what does a graph look like when the second derivative is larger than 0, but the first derivative is not 0? So that's one option. Okay? So f can go down like this. But f can also go up. What would f go up like? Well, it can either go up like this, or it can go up like that. And I'll pause again for us to have that discussion. Okay, so again we have an interesting debate, and we're looking now at what could correspond for an increasing f with a second derivative that is positive. What does second derivative positive mean? It means that the gradient f prime is increasing. So let's have a look at this one, okay, the blue. If I'm looking at this point and then that point, the derivative in those 2 points are both positive because the f is increasing. But you can understand, hopefully you can see that here the f prime is larger than that. So this blue graph does correspond for an increasing f derivative. Okay, so that's good. Let's check what about that one. Okay, again, f derivative here and f derivative here, they're gradient in different spots. They're both positive, but the derivative here you can see is less. The gradient here is less than that. Okay, so f might be increasing, but f prime is decreasing. So that does not correspond to a positive second derivative. Okay, now before we kind of conclude this bit, there's one type of graph that we didn't really look at all. Okay, both for increasing and decreasing. Straight lines, isn't it? That's also a possibility. Is it possible? Can we have a second derivative positive with a straight line? Let me ask you another way, because the answer is no. Okay? So, what do we need to say? Well, what is the second derivative of positive?
Constant, so it's not increasing.
Okay? So we saw, and this is what we're trying to understand, that positive second derivative means that the first derivative is increasing. Well, if it's increasing, it definitely can't be constant.
Okay, yeah.
So straight line are out of the option. Straight line have constant gradient. Okay? Now, that thing is called concave, or this is the concavity. Concavity, okay? This kind of graph, we will say, is concave upwards. Concave upwards.
Yeah.
Okay? I use the same kind of concave upwards. The concavity is upward. Okay? And you can kind of see that correspond to that. It's the same thing, but the difference is we don't necessarily have to be in the minimum point. Okay? So what we are understanding here is this link. Okay? Right? I'll write it down here. If, and this is like the bottom line of this, or half of the bottom line of this lesson. Okay? If the second derivative is positive, that means that the graph is concave upward. Okay? Which makes you think, probably guess, that now if we're looking at this possibility, when the first derivative is not zero, in other words, we're not stationary, okay? And the second derivative is now negative, because we're looking at this option, okay? You can probably already guess what kind of graph we're looking at. Concave down. And they will probably look like this. And now I just need to convince you that that is the case. How do I convince you? In the same way. If the second derivative is negative, okay, what's happening to the first derivative? I'll let you think about it. Okay, so everything here really is the opposite. Okay? Here we had a second derivative which is positive, meaning the first derivative is increasing. Why again? Because the second derivative is derivative of the first derivative. Okay, so if the second derivative is positive, that means the first derivative is increasing. Now we're told, looking at the situation where the second derivative is negative, well, that means that the first derivative is decreasing. Okay? And if we look at these two curves, okay, first the one that f is going up and then the f is going down, I'll show you that the first derivative in both cases is decreasing. I mean, in this case, the first derivative is always positive, but is becoming less and less positive. In other words, it's decreasing. Over here, the first derivative is negative in all cases because the graph is going down, but it's becoming more and more negative. Again, the derivative, or the first derivative, is decreasing. Okay? So if this is going to be, what will be the condition here? Okay? If the second derivative is smaller than 0, that means the graph concave down. Okay? Just like we have that local maximum, but here we don't even have a maximum. Okay? Alright? And you guys are lucky. This used to be called concave. No, this used to be called convex, and this used to be called concave, which is extremely difficult to remember. So now they just change that. That's concave upward, and that's concave down. Okay? I'll just pause here for a while. Okay, so first of all, a correction here. Yeah, Olivier, notice that should have been first derivative, not second derivative. So it was like that, but it shouldn't be. Okay, it's the first derivative that is 0. That brings us a local maximum. When the first derivative is not 0, and we're still under the condition that the second derivative is negative, it's going to call concave up or concave down. Now, the interesting and maybe a bit confusing case of what happens when the second derivative is 0. And at this point, if the second derivative is 0, actually, at this point you can't really tell. Just from that, you can't really tell. This could be actually concave up, it could be concave down, it could be a straight line, it could be many, many things. So we need to find out. Let's start with, how should I do it? I'll just pause here because I'm wasting time. Right, I'll start with a little picture. Okay? So we've got a graph. Okay? We've got a graph. Now, what is the concavity on this side, up to here? From this side to the left, on this point. Is it concave up or concave down? Concave down, right. So this is concave down. concave down. And that means that from here to the left, what can you tell me? Second derivative is less than 0. Yes. Okay. And over after the sign, what will be the concavity? Okay. And that means concave up, and that means the second derivative is larger than 0. Now let's think about it. What will be the second derivative here? Has to be. No. Has to be no. If it's positive, negative here, everywhere up to here, the second derivative is small, negative, and everywhere up to here, above here, is positive, then obviously here, the second derivative must be naught. Has to be. If we go from a negative number to positive number, you have to go to naught. So this is one possibility. I said there's actually a few possibilities, and I'll try and list them up. I'm not sure if I have time, place for all of them here, but that's the first one. Okay, so second derivative equals 0 could very possible mean this kind of point, and we did give this a name. Okay? Okay, we call it point of inflection. Okay? The point of inflection. We did discuss it a little bit. And now we're giving a proper definition for point of inflection. Okay? The point of inflection is place on the graph. I'll write it down. Place on a graph where the concavity, I don't know how to say, concavity changes. Okay? Where we go from concave down to concave up, that is the point of inflection. And every point of inflection, I'll write it down here. Okay? If we have a point of inflection, necessarily means second derivative is 0. Okay? If there's a point of inflection, that has to mean that the second derivative must be 0. Okay? And what I want to ask you now, and I kind of gave you the answer already, what about the other way around? If I have a second derivative which is equal to 0, doesn't necessarily mean that's a point of inflection. And we already discussed why. I'm going to share that with the rest. Okay? Okay. So, yeah, the question was, or what the statement is that I told you, is that if there is a point of inflection in the graph, then necessarily the second derivative is 0. And what I'm asking is, does it work the other way around? Meaning, if you find out to a certain point have a second derivative which is 0, does it necessarily mean it's the point of inflection? And the answer is no, and I'll give you 2 examples. Okay, one I already showed you a little. Okay, so we've got a function y equal to 2x plus 1. Okay, you know very well how to draw these things. It's a straight line. Okay, now let's find out the second derivative. Okay, so the first derivative is simply 2, and that means that the second derivative is 0 everywhere. By definition, the second derivative is 0 everywhere. Okay, but there's no point of inflection here. Okay, it doesn't check. There's no point of inflection. In fact, this whole graph, there is no concavity. Okay, it's not concave up and not concave down. You might actually say that the whole graph is a point of inflection because it's not concave up and not concave down. So in a way, it's not the best example, but it is. And we know that this is not the same as that. Okay, but let's look at maybe more of an intelligent example. Y equal x power 4. And I want to just ask you, Olivia, what would that graph look like? Before we look at, I'll stop here and we'll think about it together. Okay, so we figure it out, okay? What is x to the power 4? It's the same as writing x squared and we're squaring that. Okay, so we all know what an x squared looks like. It's a parabola, okay? And we're starting at the origin. If we're squaring it, we're basically just making it more sharp, okay? Right? So it's going to look like something like this. Okay? We know it's necessarily symmetrical because if I put a negative number, let's say minus 3 to the power 4 is the same as 3 to the power 4. It's just like a normal parabola but just more sharp. Okay. Now we're going to look at what happens at x equals 0. Okay? And when I say let's put it this way. Can I ask you, is this a point of inflection? Remember, point inflection is where the graph changes from concave up to concave down. What kind of concavity there is here?
Concave up.
This is concave. Is there anywhere where there's concave down? No. So there's definitely not x equals y cannot be point of inflection. All right, point P of POI, point of inflection. Okay. All right, let's try that thing. So the first derivative, what will be the first derivative? Get rid of that. Y equals x power 4, 4x power 3. The second derivative, okay. But now let's find out the second derivative when x equals 0. Because that's the point I'm interested in. So I need to put 0 now instead of x. Okay, and can you see where it's going? How much is it? 0. So we found a point where the second derivative is 0, but it's definitely not point of inflection. So we showed that this is wrong. Okay? Point of inflection means that the second derivative is 0, but the other way around doesn't work. Second derivative 0 doesn't necessarily mean point of inflection. Okay? What we would use maybe later on in university, you'll say that a point of inflection, the second derivative being equal to 0 is a necessary but not, I practiced that and I forgot again, a necessary but not sufficient condition for point of inflection. But everything said, but I should have said the other way around. A point of inflection is a necessary.
Sufficient is not necessary.
That this is necessary. Okay, so no, actually, it's actually completely different now. So we're not going to talk about it. It just works one way, but it doesn't work the other way around. Okay, we will stop with it. Okay, let's pause and we'll do a couple of examples. All right. Oh, all right. Okay. Let them come in now. Eh? Okay. Right, so actually it's really important that we do this example. We've got cubic curve, and we're trying to find the point of inflection, POI. Okay? Now, when the point of inflection, when the point of inflection, what happens in the point of inflection?
The second derivative changes sign.
Okay. And let's put it this way. You're right, you actually said better than more precise. The second derivative changes sign. It goes from positive to negative. In other words, the second derivative must be what?
No.
It must be naught. But the fact that it's naught is not necessarily a point of inflection. So, first of all, let's find suspected. We'll find suspicious, suspected is there. Suspected P of I. Okay, first we're going to find them, and then we're going to test them. Okay, test them. Okay, so we're going to find the second derivative. Okay, first derivative is. Should I do that?
Yeah.
Okay, you just test me. 3x squared minus 12x plus 5. Okay, second derivative. The good thing with these polynomials, as we're doing more and more derivatives, they become easier and easier. Okay, 6x minus 12. Correct. So now we know that that has to be equal to 0 to find the suspected point of inflection. Okay? So when is the second derivative equals 0? It's when 6x minus 12 equals 0, x equals?
Are we solving?
We're solving for x.
Oh.
I'll write it down, yeah. X equals 2. Okay, so that's our suspected POA. All right, POI, and I'll put question mark. Is it okay? Because it might not be. Like we saw with that x power, we saw that x power 4, x equals 0 was a suspicious one, but it wasn't really. Okay? So how are we going to know that? How are we going to test it? Like what you said in the beginning.
Because
we need to find out the second derivative a little bit before and a little bit after.
Because if it is a point of inflection, then it will go from negative to positive,
Correct.
positive to negative. But if it's not, then it will.
That's it.
Okay.
So we're going to write x equal to, no, let's write like this. We'll put the second derivative, no, let's write it again. Okay, x equals something, you'll tell me in a minute. X equals something, you'll tell me in a minute. Okay? And here in this column, I'm going to write second derivative. Now the second derivative, it is a suspected point, so it's 0 here, right? So we need to choose 2 points on either side, close, okay? Because we want to know if it's positive, because it might be 0 here as well, then it's not going to work, okay? Remember, in that straight line we had, for example, it was 0, but it was 0 everywhere, okay? So give me a point close to 2, but on the left side. 1.5, okay. So we're going to put 1.5, and really we want to put as close as possible, because you know what? Let's say if I put 0, it's too far away. And what could happen is that we might have had a point of inflection here, okay? But then we went too far. Okay, so I want to be as close as possible. So you know, I would even do 1.9.
Okay.
As close as possible.
And 2.1.
And 2.1. And then, how do I know the second derivative?
The derivative of the first derivative.
Well, no, I've already found
You sub in X.
you sub. Okay? So can you do that? I'll just pause here. Okay, so we found that very close to 2, but a little bit to the left, the second derivative was 0 minus 0.6. We just substituted it here. And then at 0, we obviously, it's x equal to is 0. That's how we find x equal to. A little bit beyond that, 2.1, it was positive. So the concavity does change. So in fact, it is a point of inflection. Okay? So I'll just repeat what we've done here. Okay? To find point of inflection, we find the second derivative. We make it equal to 0. Okay? Now at this point, it's just a suspected point of inflection. To really know if it is a point of inflection, we need to test it, okay? We need to test the concavity. In other words, we need to test the second derivative a little bit before the suspected point, a little bit after. As close as possible, the better. Because if we go a little bit too far, we might have missed something that happened in the graph. Okay, I'll pause to see if there's any more interesting examples. Okay, so we're doing exactly the same thing, finding POIs for y equal x power 4 minus 2. So as always, we want to find the second derivative, so we'll start with the first, 4x cubed, second derivative, 12x squared, okay? Then to find the suspected point, I need to equate that 12x squared to 0, right? Because the second derivative must be 0 for suspected point. And to solve that, very possible, we have a suspected point, suspected POI at x equals 0, okay? Is that POI? Now I need to test it, okay? So I'm going to put at x equals 0, minus 0.1, plus 0.1, okay? And substitute here and find out the second derivative. So obviously the second derivative here is 0, and minus 0.1, I need to substitute here. Okay? Because I'm trying to find what's the second derivative. So I put that minus 0.1. I don't actually even need to find the value. I just need to say, is it positive or negative?
Positive.
It's positive. I'm not even going to write what it is, okay? I'll write it. Maybe it's a bit easier. What is it? 0.12.
Yeah, but you know it's positive because it's a square. And
It's a
also
square.
going to be positive.
So this is also going to be
It's
positive.
not a point of inflection.
It's not a point of inflection because it goes from positive to 0 to positive. Okay? Now, what would that look like actually? Maybe we can try and look like, well, what is it going to look like? Well, we can try and go. This is going to lead us to the next example, 2 examples from now. If,
It's like the one we drew earlier, she should have done.
yes, just pause here for a second, very loud. Right, so I can't even remember where I was, but basically, this is concave up, okay, it's concave up. This one is also concave up, so it looks like this here, it's going to look like this there. So the concavity doesn't change, so it's not. Okay, is it a POI? Not a POI. Okay, we'll just pause here. Right, so our last example is a really good link to our next lesson. Next lesson, there's hardly any theory, but it's a lot of practice. I'm going to give you a function, certain function, and we just need to draw it. Okay? So it's using all the tools we learned about concavity, increasing gradient, positive gradient, negative gradient, point inflection, added with your y-intercept, x-intercept. Basically, I'll give you a function, we need to draw it. Okay? Difficult function. And this is a good link for that. So I've got some information on the function at 2, when x is equal to. Okay? So the first, and I want to draw it in the vicinity. Draw the function, draw f close to 2. Why is just close? Because, well, I don't know what happens later. I just have a lot of information at 2. So the first level, you would learn that in grade 8. Okay, when x equal 2, y is equal minus 1.
Yeah.
So this is 2 minus 1. Okay, so I know there's a point there. Okay, now that's what you learn in grade 8, maybe grade 9. Now, you already learned last year, okay, about the first derivative. The first derivative is positive. What does it tell you about the graph? It's close at 2.
Increasing.
It's increasing. Okay? Because if the first derivative is positive, that means it's increasing. Okay? But that means it can either increase like this. Let's draw different colors. It can either increase like that, or it can increase like that, or it can increase, let's do it, like that.
Well, you have the second derivative.
That's why we need the second derivative. Okay, so at this point we have 3 possibilities. We need to choose. The second derivative is negative. So you gotta ask, in your mind, the back of your mind, you gotta ask, all right, if the second derivative, if you know something about the second derivative, that tells you something about the first derivative. Is it? I know that the first derivative is positive, but is it increasing or decreasing? It's decreasing. Because if the second derivative is negative, that means the first derivative is necessarily decreasing. In other words, which curve is it going to be? Green, black, or red? Which one has a slope?
It's not the green.
It's not the green, because they're the first derivative.
Probably the black.
I'll be black, that's constant. So fantastic, good job.
Thanks.
So that helps you draw it. Okay?
Was that all that we drawing?
Yeah, because we don't know what happened then. But it's a good start. Next time we'll learn how to do the whole curve. Obviously we need a bit more information. Okay? Yeah, I'm gonna stop here. Good work.